Mastering the techniques of brazing and soldering are essential in producing leak-proof sealed system joints. Both techniques can be performed with oxyacetylene or air acetylene. Both techniques melt a filler metal to form a metallurgical bond. The difference between them is merely a matter of heat. Soldering is performed at temperatures below 840 degrees Fahrenheit, and because of that, requires the use of flux to ensure good capillary action. Brazing, also called silver soldering, takes place at temperatures above 840 degrees, but below the melting point of the metals being joined. The filler metals used at these temperatures on copper contain phosphorus and promote good capillary action, so brazing copper to copper can be done without using flux. The trick to creating a perfect braze or soldered joint is in evenly heating the tubing and the connection to the correct temperature without overheating. Overheating the metal causes many problems. Capillary attraction is a fundamental principle in brazing and soldering and is the basis for sound joints. When a joint is prepared and heated correctly, the filler metal will melt when it contacts the base metal, and capillary attraction will draw it into the narrow space between the pieces. It will actually fuse into the base metal to form a metallurgical bond or third alloy. Capillary attraction is a delicate force that depends on wetting to pave the way into the joint. Wetting is how the filler metal moves through the joint. A molten drop of filler metal takes the shape of a drop because the molecules within the alloy are attracted to each other, but they have a stronger attraction to the base metals being joined. So, as the filler metal enters a joint, the natural curve is broken as the alloy is first attracted to one wall of the base metal. This is called wetting. The opposite wall of the base metal is then wet by the filler metal. The filler metal then reforms its natural curve. As long as nothing disrupts this process, it continues as the filler metal travels the length of the joint. But if the metals are not properly cleaned or are overheated, wetting may not occur and the capillary attraction is lost. Most services prefer brazing because it's quicker and doesn't require using flux. Brazing is quicker because the flame is hotter. So it's important when brazing to be careful not to overheat the joint. Brazing refrigeration tubing is best done with a number 2 tip. Begin by cleaning the pieces to be brazed. Wipe oil, grease, or dirt from the tube and fitting. Then use an emery cloth, tube cleaner, or cleaning pad such as Scotch-Brite. Cleaning is critical because it removes oxides that would disrupt wetting of the surface by the filler metal. Flame adjustment is always important. When using oxyacetylene, a neutral flame is best for copper. A neutral flame is produced when the ratio of oxygen and acetylene is approximately 1:1. When a torch is lit, the initial flame contains an excess of acetylene. This flame is called a carburizing flame because it deposits carbon on the workpiece. Carbon on the workpiece would inhibit wetting. To produce a neutral flame, add oxygen until the inner feather all but disappears. Adding too much oxygen, however, will produce an oxidizing flame, characterized by a sharp inner cone. An oxidizing flame increases surface oxides that also prohibit wetting. A neutral flame is needed because it imparts no chemical reaction to the base metals. Use a filler metal that contains phosphorus. Phosphorus is a deoxidizer and makes the alloy usable without flux on clean copper. Proper heating is critical to making good joints. The majority of leaks can be traced to improper heating. The reason is simple. Joint strength and soundness depend on drawing the filler metal into the capillary space. Filler metal will not flow into the joint unless both parts are at brazing temperature. Improper heating ruins capillary action, so that filler metal just piles up around the outside of the joint. Over a period of time, system vibration will cause a leak to develop. How do you evenly heat both parts to brazing temperature? If you heat only the fitting, then you must conduct heat through an airspace, and air is a poor heat conductor. If you instead first heat the tube, you take advantage of copper's excellent conductivity and draw heat inside the joint. Then apply heat to the fitting, keeping the torch in constant motion to adequately heat both the tube and the fitting. But don't overheat. Overheating causes a variety of problems. First, it oxidizes the base metals, and the oxidation interferes with the flow of filler metal into the joint. Second, oxides inside the joint will flake off and potentially block the cap tube. Only a nitrogen purge will have enough pressure to loosen and eliminate all of those oxides. Once the parts have reached brazing temperature, apply filler metal and always apply it to the opposite side of the joint from the flame. The base metals will melt the filler metal and the capillary action will draw it into the joint. Never use the flame to melt the filler. Filler metals will start melting below brazing temperature, but will not become fluid until it reaches brazing temperature. So, if the base metal is too cool, the filler metal will stick but not penetrate. As the filler melts, watch for it to be drawn into the joints. That's a good confirmation that you have reached brazing temperature. Move the flame around the coupling to draw molten alloy into the capillary. If necessary, add filler metal to other points to fill the joint. Capillary action even works on a vertical joint. First, heat the tube, then heat the fitting. Keep the torch in motion to evenly heat both pieces. Then apply the filler metal. For joints in this position, direct the flame away from the joint to draw alloy into the joint. It's important to understand that a large buildup or fillet around the outside of the joint is not needed, nor is it an indicator of a good joint. It's usually just a waste of material. A small concave fillet is preferable, unless an additional cap is necessary to promote moisture runoff. This can be accomplished by reducing the heat and adding a fillet. Anytime you need to protect part of the tubing from the heat source, use a cold shield gel that is designed specifically for that purpose. Never wrap tubing with a wet rag on a 134A system. The heat will draw moisture into the tubing, contaminating the system. When brazing steel or brass, or brazing these metals to copper, you must use the appropriate filler metal for those base metals. Never use a phosphorus-bearing alloy to braze steel. The joint will be brittle. Also, take care when brazing copper-coated steel. If in doubt, use a silver brazing alloy. You'll need to use a chemical flux with these base metals to dissolve oxides and prevent them from reforming during heating. Flux goes through changes during heating, and these changes are a visual clue to when parts are at brazing temperature. At 212 degrees Fahrenheit, the water boils off. At about 600 degrees Fahrenheit, the flux begins to bubble, and at 800 degrees Fahrenheit, it starts to melt and become active. Notice the clear protected area under the flux. At approximately 1100 degrees Fahrenheit, the flux is clear, and we're ready to apply our filler metal. When brazing copper to steel, remember, steel does not conduct heat as rapidly as copper. Generally, directing more heat to the copper will bring both pieces up to temperature. Watch the flux to ensure the parts are getting even heat. As in all brazing jobs, as you add filler metal, watch for it to be pulled into the joint. It's important to remove flux residue from brazed assemblies. After brazing, wipe the joint thoroughly with a wet rag. But in dissimilar metal joints, let the pieces cool prior to cleaning. Otherwise, the different thermal contraction rates might cause the braze to crack. Refrigeration connections can be easily soldered at lower temperatures. There are many low-temperature fillers that produce joints with excellent strength and ductility and can be used on copper, brass, and steel. The big advantage to soldering is that the low heat prevents scale buildup inside the tube, so a nitrogen purge is unnecessary. Also, you can solder near valves without applying a protective coat of gel. The filler metals used at these lower temperatures require the use of a separate flux material. Be sure to clean all flux residue from the joints when finished. You should always stay within federal guidelines when recovering refrigerant from a sealed system. This program does not cover those guidelines, so if unfamiliar with them, please take the time to review them. Recovering refrigerant with a pump requires tapping into only the low-pressure or evaporator side of the system. A variety of approved pumps are available and differ in their use from model to model, so it's a good idea to review the manufacturer's guidelines for the pump you're using. After tapping into the system and making all the appropriate connections, open the line tap service valve. Start the pump and then open the valve for the waste tank. Most domestic refrigerators hold only 3 to 7 ounces of refrigerant and take about 5 minutes with a good recovery pump to recover the refrigerant from the system. If you are using a recovery pump and tank, you'll need to get a sample of oil out of the old compressor to see if the system has been contaminated. The procedure for recovering with just a bag depends upon whether or not the compressor is functioning properly. If the compressor is functioning properly, you'll use it to draw refrigerant from the low side and push it out of the system on the high side. Tap into the high side at the dryer, where the refrigerant should be mostly in liquid form, making for a better recovery. Connect a hose from the service valve to the bag and open the valve. Start the refrigerator and let the compressor run. It will draw all of the refrigerant from the low side and pump it out the high side. It's very important to understand that recovery bags are designed to hold a specific amount of refrigerant. The bags are large in volume so that when gravity feeding refrigerant from a system with a dead compressor, the bags will accept all of the refrigerant from the system. While the bags may appear to be able to hold more than their specified capacity, you must never exceed that capacity. Doing so by as little as 2 ounces will usually rupture the bag. Let the compressor run for at least 10 minutes. As refrigerant travels into the bag, there's a certain amount of compressor oil that travels with it. This is a great opportunity to look at that oil and get an idea as to the condition of the system. As oil starts to overheat, it will begin breaking down and turn to a real dark brown color. Look around the service valve. If you see dark oil instead of clear, then you probably have a contaminated system. This system of recovery works quite well as long as you have a good functioning compressor to work with. If you're using the recovery bag and do not have a functioning compressor, you will have to tap into both sides and let gravity drain the system. Once you've made the connections, open both service valves and then the manifold. It'll take at least 15 minutes to gravity feed refrigerant out of a system. You should see a slight raising of the bag as the refrigerant goes into it. Look around the service valve and in the recovery bag. If you see dark oil instead of clear, then you probably have a contaminated system. When using a recovery bag, you'll still have to pump the contents into a waste tank when you return to the shop. Hook the bag up to the pump, just as you would if you were recovering with a pump to a tank. Turn on the pump, then open the valve.